Okay, so let's take a look at the next set of examples where the directions ask us to evaluate each integral. And we're going to be evaluating these using areas of geometric shapes. Okay, so for number one, we have the integral from 1 to 3 of 4, which we're integrating with respect to x. If you want to use the properties for a constant function, that's fine. If you want to draw a graph representing this, that's okay as well. So the function y is equal to 4 is going to look like so. In between the x values of 1 and 3 are going to look like that. So that's going to give us the area of the rectangle, which is the length of the base, which is 3 minus 1, times the height. The height of the rectangle is 4. So that becomes 4 times 2, which makes that integral then equal to 8. Okay, we look at number 2. With number 2, we have the integral from 1 to 4 of x plus 1. Now, you guys are going to want to draw these graphs accurately. So x plus 1, graphically, that's going to be the linear function y is equal to x plus 1, which has a y-intercept of 1 and a slope of 1. So graphically, that function is going to look like this. If we want to calculate the area enclosed by that curve in the x-axis from 1 to 4, our resulting area is going to look like this shape right here, which is a trapezoid. Okay, so the area formula for a trapezoid is 1/2 the height. So the height is going to be this segment right here, which is the length of our interval, which is going to be 4 minus 1, which is 3. And then our shorter base is going to be this segment here in black, which is going to be 2, plus our longer base is going to be this segment here in red, which that is going to be 5. So 2 plus 5 is 7, times 3 is 21, and then we're dividing that by 2. So that area is going to wind up becoming 21 over 2. Okay, for 3, you have the integral from -3 to 3 of rad 9 minus x squared. Now, some of you may not know what the graph of that function looks like. So I'm going to manipulate this equation a little bit and maybe put it in a form where you might be able to recognize it better. Okay, so I'm going to say that y is equal to rad 9 minus x squared. Well, if I were to square both sides of the equation, that would make y squared equal to 9 minus x squared. And when I add x squared to both sides, we get x squared plus y squared equal to 9. And when you look at that equation, that might be more familiar to you. Okay, that's going to be the equation of a circle centered at the origin with radius 3. Now, if we took that equation of the circle and worked backwards, so like going to this step and then to this step, going from the middle line to the top line, when you take the square root of both sides, y would be equal to plus or minus rad 9 minus x squared. So the positive radical there is going to be what gives you the top half of that circle of radius 3. The negative radical would be what gives you the bottom half of that circle. So since we only have the positive radical, this function is going to be the top half of the circle centered at the origin with radius 3. Okay, so graphically, that function is going to look like this. Okay, so if we want to compute the area enclosed by that semicircle and the x-axis, The area is going to be 1/2 the area of the circle, which is 1/2 pi r squared. The radius is 3, so that's 1/2 pi times 3 squared, which becomes 9 pi over 2 for that area. Okay, so again, we're just using like area of geometric shapes to compute the value of our definite integral. Okay, for 4, you have the integral from 2 to 4 of the absolute value of x minus 2. Right, so the absolute value of x minus 2 is going to be the absolute value of x shifted 2 units to the right. Okay, so graphically this function is going to look like so. So if we want to take the integral from 2 to 4, that's just asking us to find this enclosed area right here, which that area is in the shape of a triangle. So area of a triangle is 1/2 the base times the height. The base of that triangle is 2. The height of the triangle is 2. So that area winds up becoming equal to 2. Okay, I want you guys to give 5 and 6 a try. So for 5, you have the integral from 1 to 4 of x minus 2, which you're integrating with respect to x. And for 6, you have the integral from -1 to 1 of the quantity 1 plus the square root of 1 minus x squared, which you're integrating with respect to x. All right, so pause the video, give both of those a try, and then you can turn it on after to see how you did. Okay, so let's check and see how we did with these. So x minus 2 graphically is going to look like this. So this has a y-intercept of -2. And the graph has a slope of 1, so graphically your line is going to look like so. And if we want to take the integral from 1 to 4, then that's going to compute that area and that area right there. All right, so what I actually want to do in this instance is I'm going to take the integral from 1 to 4, and I'm going to break it up into the integral from 1 to 2. And the reason I'm going to do that is because that area lies below the x-axis. That area is going to be counted as negative. Okay, plus the integral from 2 to 4. And since that area lies above the x-axis, that area is going to get counted as positive. Okay, so the area that lies below the x-axis is going to be negative. It's in the shape of a triangle, so it's going to be 1/2 the base, which is 1, times the height of the triangle, which is 1. And then the second area is also a triangle. It lies above the x-axis, so we're going to count that area as positive. So again, it's 1/2 the base. The base of that triangle is 2 times the height, which is 2. So this winds up becoming -1/2 plus 2, which makes that area equal to 3/2. And again, that should make sense. That net area should be positive because there's more area above the x-axis than there is below. Okay, when we look at 6, number 6 is the integral from -1 to 1 of 1 plus the square root of 1 minus x squared. Well, that should look similar to what we had in example 3. We have the square root of 1 minus x squared, which should be the top half of a circle centered at the origin with radius 1. But then we're adding 1 to the function, which is going to shift that graph up 1 unit. Okay, so what we have graphically here is we have a semicircle, so the top half of a semicircle with radius 1 shifted up 1 unit. Okay, so we've got our graph looking like this. Whoops, I don't know why that came out like that. We'll fix it. So looking like this and this. Okay, so this is the semicircle part. And that semicircle is going to lie on top of a rectangle. So if we want to compute that entire area, then that's going to be equal to the area of the half circle, which is going to be 1/2 pi r squared. So the radius of that circle is 1, plus the area of the rectangle that it lies on top of. So the area of that rectangle down below is going to be the base, which is 2, times the height, which is 1. Okay, so this first calculation here is going to give us the area of that half circle, and then the second calculation is going to give us the area of the rectangle that lies below. Okay, so when we simplify this, this winds up becoming pi over 2 plus 2. All right. Last two examples. So directions here say to evaluate if a is greater than 0. For number 1, we have the integral from 0 to a of 4x, which we're integrating with respect to x. Okay, so again, here we can draw ourselves a picture once again. So we're going from the x values of 0 to the x value of a. If I plug a into the function 4x, the output is going to be 4a. So the 2 points on the graph of 4x are the point 0, 0. When I plug 0 into 4x, the output is 0. And then when I plug a into 4x, the output is 4a. So graphically, our function is going to look like so. If we want to compute that area between that line and the x-axis, we have the shape of a right triangle. So area is going to be 1/2 the base. So the base of that triangle is going to be a times the height, which is 4a. So that's 4a squared divided by 2, which is 2a squared. Okay, you guys give number 2 a try. That's the integral from a to 2a of x plus 1, which you're integrating with respect to x. Okay, so function x plus 1 has a slope of 1, a y-intercept of 1. If we take the integral from a to 2a, we want to find the y values that correspond to these x values. So we're going to get those by plugging a and 2a into our function. So when we plug a into our function, the y-coordinate is going to be a plus 1. When we plug 2a into our function, the y-coordinate is going to be 2a plus 1. So graphically, when we compute that area is going to be in the shape of a trapezoid. So our trapezoidal area formula is going to be 1/2 the height. So the height is going to be the length of our interval here, which is 2a minus a, which is going to be a. And then we're going to multiply that by the sum of the bases. So the first base in green is going to be the y-coordinate of that point, which is a plus 1, plus the second base at 2a is going to be the y-coordinate there, which is going to be 2a plus 1. And then if I just want to simplify this, that's going to become a over 2. And then when I combine like terms in the parentheses, we get 3a plus 2. Okay, and that's going to give me my area of that trapezoid in terms of a. All right, so that wraps up section 5-2. We'll take a look at 5.3 during the week. So again, make sure you guys have this homework assignment done before our next block meeting, either on Wednesday or Friday of next week. All right, hope you guys are having a great weekend. We'll see you in class tomorrow. Take care.